coming tomorrow. But for right now, we can't totally not go into chapter 8 at all. We can't totally ignore the calendar. But Friday, no chapter 8 at all, just the calendar. And then, Max, I'm going to have you try it on Friday too, but if you can come in and we talk about it, let's see if we need you ready.
Okay, thank you.
Yeah. So here we go. Section 8.1. Rounding f of x equals ax squared. How many of you guys have seen this curve before? Raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. Okay, a few. Ax squared. Nice thing is there's no bx and there's no c. It's just him, monomial, one guy. But something that you guys need to know, in chapter 7 when we were factoring, we saw all sorts of different dudes. On your test, if you were to pull it out right now, was 2 the highest degree?
No.
No. Like you guys had like 4th degree ones that you had to like pull out, and there were some GCS that, okay, 2's not the highest they go. So why is this one just say ax squared? Now some of you say 2. If I can get you to change that to ax squared or to the power of 2, man, that would make a world of difference. Because if you say ax2, I don't really know if I'm listening to you. I have no idea what you're saying if I kind of know math. Because literally if you say ax2, so a times 2, or ax plus 2, or ax, I don't know what's going on. So don't just say 2, okay? We got to get that 2 up into the exponent. I'm just hearing some of you talking math and speaking these equations, and they're not making sense when you say it out loud, and they want your words to make sense. So ax squared or ax to the power of 2. Anyway, these guys, quadratics are their name. Quadratics are their name. Their shape is what we call a parabola, which is that little U guy. Here we go. The parabola is the name of this graph. And there's a few different things that we're going to talk about as far as the different pieces of their equation. But the first thing I want you guys to kind of add into the notes today is that the degree will always be 2. For quadratics, that's the highest degree. As you guys are kind of setting up notes for today, let me find the marker. Oh my goodness, going on. I'm going to write up an equation that was super important to you guys in this other one last year. Those of you that were here. This guy is super important in Algebra 1A. Who is that? Okay, slope is there, right? We have m being a slope. Does anybody remember who b is? He's like y. He's a constant, he's a number, and he has something to do with the y-axis.
Now if it goes up or down.
Intercept. It's the intersection of the y-axis. So it is an x value. Well, no, actually it's a y value. X is 0. But he is what we call the y-intercept. But do you guys remember this equation? What shape was his graph? It was like a... I heard it, so I'm writing. It was a linear function. Slope-intercept form of a linear function of a line. And there was also, there were some weird forms. There was ax plus by is c, standard form of a line. There was the one that most of you guys hate, but my older kids, they have to just become best friends with, y minus y1 equals n times x minus x1. Point slope form of a line. But what do you notice? Here's my question. What do you notice about the degree of x over there? What's his degree? You did your chapter 7 corrections. There was that degree question for those polynomials. What does degree talk about? What's the biggest and degree? What are you looking at?
Number.
The x exponent, the x power. So the highest one. Well, guys, what's the only power of x in this one? Where's the only x even present? Right here, right? So what degree does he have? What power does he have? What exponent does he have? Just one. All lines have degree. All linear functions are polynomials with a degree of 1. He's the most basic. Well, not the most basic. I guess y equals c. That's just a straight horizontal line. He's the most basic because there's no x. Degree 0. But then these diagonal lines, that's degree 1. You start being able to go here. And degree 2 says, aha, let's bring in a curve. Now, in real life, if math is supposed to be used to model things. Have you guys ever heard that math is used to model like real life situations or scenarios? Is anybody in chemistry this year? Okay, ooh, that's good. There's a lot of math in chemistry. So we're still learning the fundamentals. But in chemistry, there's a lot of math that's modeling like how the science works, how the reactions work, how everything kind of ties together. Math is kind of, oh, hey, a language with which God has written the universe. It's on my wall every single day. In a sense, math is a language that all these different economists and scientists and physicists and astronomers and all these people can use to explain all these concepts as to how things are working and moving and changing. Stock markets, oh my goodness, there's so much math in economics. It's crazy. Like calculus is all over the place, kind of like under the scenes stuff. But if math is used to model the real world, if math is the language with which a lot of people are able to explain what they see and even to predict what's going to happen. Did anybody come today with a sweatshirt because they knew it was going to rain?
Yeah.
Why'd you know it was going to rain?
Because
No.
the weather said it.
The weather said
felt
so.
it.
Now, some people just smelled the air, saw the clouds last night. But does anybody look at the weather every morning?
No.
Or your parents?
No.
But how do they know what's going to happen? It hasn't happened yet. There are meteorologists that predict, and they predict based on patterns, and the patterns they have to have, a lot of it now is computer programming. There's a lot of stuff that has been programmed for computers to help us. But guys, there's a lot of math behind it. Why am I saying all of this? This is stupid. Pause. Do you think everything changes or moves in lines? No. Lines say the slope is always the same, which means the rate is always the same, which means if you're in the car, after 1 minute, you've gone the same number of miles as after 2 minutes, and the same number of miles as after 3 minutes, and the same number of miles as... Wait, does your speed ever fluctuate when you're driving?
Yeah. Yes.
If you're driving in the car, and some of you eventually want to be driving the car, right? You're not going to be going one speed, one slope. It's going to be changing, and as soon as your rates start changing, you have curves. This is the very, very beginning of realistic graphing. Some things move in lines. Most things move in curves. There was a basketball game last night, right?
Yeah.
Question. If you're trying to shoot in a line to the basket, is it ever going to work?
No. Yes.
But if you shoot in a parabola, now you got to get your elbow in, you got to get that nice arc, right? But maybe a nice like bank shot, but right? You can't do it in a. If anybody tries to shoot in a line, what's going to happen? It's going to come back and pop you in the face, right? Or pop someone else in the face. Either way, it's going to be bad. This is how wait a minute. That's not how it works. We would need one of these that was maybe going the other direction. Okay, whatever. We can do that with math. We can flip it around. We can shift it all over the place. But parabolas are how a lot of things move. Anything that's thrown is going to be a parabola. Unless you're trying to like beam somebody, then maybe it's a line. But even then, it's going to eventually start to arc because of something we call gravity. It's going to start to have curves. So I know it might just seem like some stupid whatever, it's a math equation, blah, we have to memorize it, but it actually is like the beginning, opening the door of, we can actually start to show stuff that happens in life with math. And the whole reason I brought the weather report is because if we can start showing how things are moving, we can predict where they're going to go. And there are whole fields built on predicting what's going to happen. Financial advising, super lucrative, but it's all about thinking ahead. Okay, so who's this A guy? Who's this A guy? What do you guys see in A on the page? I'm saying when A is negative, when A is positive. Who's this A guy, and why are you having a conversation all the way across the room? So, A is a coefficient. Nice terminology, I love it. It's a coefficient. It's a coefficient of x squared. And some of you saw that word coefficient in your Chapter 7A test corrections because you were labeling the leading coefficient. A is the leading coefficient of any quadratic written in proper form because that head guy is going to go first. Descending order, right? So A, he's the head guy. And if A is negative, I'm going to have, there's silly ways of remembering it. But I am going to have a concave down is this snazzy math terminology for what the graph looks like. AKA, instead of being a smile, it's going to be a frown. Is there a way of remembering that? It's a frown, it's negative. Oh. And it's a smile, it's positive. Can we talk about like personality and dispositions and all that sort of stuff? Sure. But concave down like a frown?
Down like a frown.
And A is negative. Huh? Have a negative outlook on life. You're probably not always smiling. Well, sometimes you're smiling more, but that's a whole different psychological study. So, concave down. Concave down. But also, you're going to have this thing that's called, let's see, how do I put this? We're going to just say that it has a maximum. Anytime your parabola is concave down, you're going to have what's called a vertex, and it's going to be a maximum, which might seem kind of like, okay, whatever, yeah, there's a maximum, highest point. But that whole idea of a highest or a maximum is super important in life, because in life, when you have a max, if you're trying to maximize your profits and minimize your costs, this idea of a maximum is super important. Now, this one has a maximum. What's this parabola? Well, first of all, hold on. If this one's concave down like a frown, what's this one going to be? Yeah, concave up. And sometimes in like physical science and things like that, you talk about concave lenses and convex lenses, and there's like all these different curvatures like going in or going out. We don't have to worry about that. In math, we just say, concave means curved. And we just have to figure out what kind of curve. Is it a down curve or an up curve? And there are functions, guys. This is just the beginning. There's so many functions out there. Actually, I can show you if I come over here. My calculus kids at the very beginning, maybe some of you saw this on the wall at some point. At the very beginning of the year, they have these cards that they build as far as things to have memorized. And this was a review card, but it's stuff that, well, we're not quite there. You guys see all these graphs?
Yeah.
These are the basic graphs that the higher maths are built on. Hey! There you go. There's a horizontal line. Y equals C, degree 0. Oh, now degree 1. Uh-oh, we don't know any of these guys. Wait, yeah, we do. So we're just kind of scratching the surface of opening the door to all the rest of these. But, concave up. This is how we just talk about curves. So there are some different ways of curving, but for right now, concave down, concave up. And if we have a concave up, instead of a maximum, we're going to have a minimum. Can anybody think of something in real life that you might want a minimum of? Like profit, maximize those, yeah, money coming in. What would you want to minimize? Taxes, maybe. Some people do that legally and illegally. What else? Spending, minimize your spending. That's a good idea. Minimize cost is what like economists would say. Maximize your profits and minimize your costs. Anyway, there's context for wanting like the highest of something. Yeah, bring the money in, and then the lowest of something, spend as little as possible. Then you have more money in your account, right? Well, some people. Yeah, for sure. Economics is a really tricky field. It's a cool field, but tricky. I'm going to zoom in on this guy right here so we can talk about a few other parts of him. But technically, if you want, you can take the parabola you've already drawn, because you've already drawn a parabola, and you can label a few things like the part of, well, hold on. Doesn't it kind of depend on your perspective? Couldn't you be traveling this way from the valley and so you'd be increasing heights?
No.
Or traveling this way and you'd be decreasing?
No.
No, because in math, we read like in English. And in English, don't we read words from left to right?
Yeah.
Okay, so same thing with the graph. The number line moves from negatives to positives. We're only moving left to right. And as we are, I just want you guys to find one of your parabolas and then find the part that's going down and just say decreasing. It's a snazzy math term. But when we say the function is decreasing, technically what we're saying is that the heights are decreasing. You guys know, well maybe you don't know, I was gone last Friday because Mrs. McRae, Mr. Graff and I went to a math conference down in Palm Springs Friday and Saturday. From 5 a.m. Friday morning, we started driving till we got back at 8:30 p.m. on Saturday. It was super busy, super full. But I was sitting in calculus workshops, not just them, but I was sitting in some calculus teacher workshops. And they were like, oh, if only kids could figure out in Algebra 1. Hey, that's where you are. In Algebra 1, that when we say decreasing, we mean the heights are decreasing. So I'm writing it, letting you know the heights are decreasing. And probably in your head, you're like, this means whatever. But maybe it'll help somebody. So when I say the function is decreasing, I mean the heights are decreasing. When I mean the function is increasing, I mean the heights are increasing. Which, isn't that so straightforward if you look at it, right? The heights are going down, heights are going up. If you were hiking a mountain, you would feel it. You would feel the elevation change. Get to your valley and then go back up. The vertex we've already talked about is that point at which these two increasing, decreasing branches come together, otherwise known as the minimum in this example. We're just labeling stuff, getting used to this parabola guy. And then here's a weird one. It's a dotted line that you might not be able to see, and it's called the axis of symmetry. Now, you guys see the axis of symmetry, x, and the x of the vertex. What's true about both of those? Yeah, they're both the same, yeah? And that's going to be a really cool trick that's going to help us when we start answering questions about these parabolas. So, you guys, I think, have seen the word domain and range before, but it's been a while. I didn't teach it to you, it was last year. And I have a silly way of remembering it. So I don't remember teaching it to you this year. Did I teach it to you yet? Domain goes with x's and range goes with y's. Domain goes with answering the question of how far left to how far right. You're thinking the x-axis and how left can you go and how right can you go. Domain is answering like an interval. For range, the y's are the heights. So how low do you go? Maybe you could say how far down to how far up. That might be an easier way of putting it. How far down to how far up. For lines, it was kind of straightforward. It was kind of basic because for lines, usually you go forever left, forever right, forever down, forever up. So it's just kind of forever in all the different directions. But once you start talking about parabolas, it's not forever anymore, at least not always. Because no matter how hard you throw that ball, there's still going to be a maximum height it can hit. It's not going to go soaring into the atmosphere, right? Or no matter how hard you throw a yo-yo down, there's still a certain finite length of that string and it's going to bounce back up. Hey, those are both parabolas. So, we have to review something to do this whole domain and range thing. One thing that we're going to have to review is inequalities. Although, there is one that's going to be kind of nice. If we zoom in on this graph for a second to try to answer these domain and range questions, and guys, you see these little arrows at the end, right? Which means go on forever and go on forever. How far left is this thing going to keep on going? Forever. Because the parabola's going to keep on getting higher and higher and higher and higher as far as increasing the heights, technically both directions, but it's going to keep on rising. So if I were to go to -6, would it hit somewhere? Yeah. -10, would it hit somewhere? Yeah. So how left does a parabola go? Forever. How right does a parabola go? Forever. And in math, we use a really snazzy term to talk about that, all real numbers. Which means forever left, forever right, in answering that question for domain. Oh, Jeremy, do you have the pencil today? Oh, you do? Good. Let's go and make sure we get this down. Super important. Maybe there's a really snazzy symbol that represents. What's that snazzy symbol for all real numbers? Oh, the sideways A? We could do that one. Oh, infinity. That's what you're thinking of. Okay. I was like, whoa, you've seen that symbol. I mean, that's a symbol in math, but I didn't think you would know it. You could say infinity, or In English, have you guys ever seen that like start a new paragraph sign? Everybody's been like proofreading?
Oh, yeah.
There's something kind of like it in math for all real numbers, but it's with an R instead of a P. So it's not like a new paragraph, it's all real numbers. You can just learn some really snazzy notations that mathematicians use. But even though the how far left and how far right doesn't stop for a parabola, it goes on forever, the how high and the how low definitely does. So for this one up here, do you guys see how this parabola went down to -2 and that's it? Is it ever going to go below if it just keeps on going forever?
No.
No. So how low does it go? -2. How high does it go? Forever. And how do we write that with math symbols? We say, well, inequalities. Y is going to be greater than or equal to -2. Domain, all real numbers, no big deal. Almost every parabola, at least basic one, oriented up and down, it's going to be all real numbers. That's something you can kind of bank on. Bank on, take to the bank, take to the bank is like making it solid or secure. Although, this day and age, some banks aren't so secure. But range, this one's going to change. It's either going to have a highest or it's going to have a lowest based on whether it's a concave up or a concave down. But we are going to have to use inequalities like greater than or equal to's, less than or equal to's to say how low does it go, how high does it go. Decreasing, if we were to actually state like where it's decreasing up here, it's decreasing everywhere before, let me get back to an entire page, everywhere before the vertex. And in math, we would show that with x less than or equal to that -1. And increasing is everywhere after that vertex. Now, actually, I have to take away the or equal to. I have to take away the or equal to or else. If I put an or equal to in both of these, I'm saying at -1 it's doing both. And doing both doesn't really make sense. You're kind of just like stuck in the valley, right? Like you're going down the mountain if you're going this way, and then you're in the valley, and then you're going up the mountain. When you're at that middle point, when you're at that vertex, you're not really going down or up. You're kind of just stopped. That's like a huge calculus concept that we're not going to go into today. But for those of you guys that are thinking of like throwing a ball in that parabolic arc, there's a physics concept that says at the very top, right before it starts falling, it actually momentarily stops. Now you don't see it because it's so fast, but it increases up to that max, it momentarily stops, and then it decreases. And that's kind of one of the reasons that I have to take away that or equal to thing. At that vertex, and it actually stops. Okay, we've analyzed this guy. Right, left, forwards. Okay, we've analyzed them. Now we need to see what's coming in homework, okay? In homework, you're going to be given one of these parabolas. That's the snazzy name of a quadratic. A function that has some sort of square in it. Now, technically, this is one of those ones that you guys are factoring in your test, those trinomials, because he's been moved all over. But we just get to look at his graph and talk about him and answer these questions. Now, you guys have your notes right there that tell you how to answer the questions. Okay? So let's see if we can kind of mimic it in order to follow this example. Now, it might be kind of hard to see this graph. Can I zoom in just a little bit and label some stuff for you? Can you guys tell me the ordered pair of the vertex? Remember, the vertex is either the highest or the lowest. So for this one, it would be the lowest. What's the ordered pair, the x and the y, guys? -2, not -2. X first. What's the x? Yeah, good. We have to go to the right 2, and then what's the y? Okay, so first thing we have to figure out is what on earth is that vertex? Isaiah, hello. Isaiah. So we have a vertex of 2, -3. Now, look at your notes. Domain. Domain. Because all real numbers work for this one, too. Is it going to keep on going? Forever left, forever right. Oh, sweet. What do you guys want to do? The infinity symbol or that double R?
Infinity.
Okay, infinity. Is that easier? Sideways 8?
And this.
Double R works, too. But sideways. Okay, the range. For this one, how low does this one go?
3.
A height of -3. So in a sense, you could think of this being the ground. You dug a hole in the ground, and you're dropping something down into it, or like swinging something out of it. The lowest it's going to go is at -3. So wait, how did we write it for the other one? Y, because those are the heights, needs to be greater than or equal to, because it has a point there. -3. Perfect. And what? No, you're okay. Increasing, decreasing. Do you guys see in the notes, do you see that we're going to use x's for that? Right? But question, where is the graph increasing? Is it increasing to that we have our little x right here, the 2, right? We have our x. Is it increasing to the right or to the left?
Right.
Okay, so it's increasing as I move to the right, well, I'm going to be moving up my mountain. I'm going to be increasing. So wait a minute. Do you remember that the arrows also show what the inequalities will be, right? You're moving to the right. Oh, look, to the right. You can kind of follow the little tail of the arrow. And that's going to be 2. So then what do you think decreasing? Wait. Didn't I make a big deal about how we're not supposed to do or equal to? Okay. Sorry, that whole physics concept thing. We got to take away the or equal to. But how am I going to explain where it's decreasing? Opposite. So instead of pointing to the right, I'm instead decreasing, right? He came down the mountain on that side, so less than 2. Okay, this doesn't seem that bad, right? Domain, range, how far left, how far right. Range is how high, how low. And I think you can kind of follow the patterns of the example that we just did. So let's see if it gets any worse. What about to give you this guy? What's changed?
Pointing out.
Oh, now we have something in flight, right? Something that's going up and then coming back down. Now I'm going to help you out because this one I just kind of zoomed out a little bit. It's vertex, the very first thing we need to figure out, because we kind of use it for all those answers. The vertex is going to be, not a min this time, it's going to be a max. And it's at the point -3, 7. Okay. We're still going to work together on it. But I want to hear your guys' ideas. I kind of led you filling in for this one. Bless you. Can you help me out on this one? Does anybody have an idea for what they think the min is? Why? Because it's going forever? Left and forever? Oh, sweet. Let's use the other symbol just because people can use either one. You can write the words or you can use a symbol. Remember how efficient? We're lazy but efficient. We have to make sure the meaning's there, but in a fast way. Okay, range. And I use greater than or equal to, which will go forever.
Less than or equal to 7.
Okay, hold on. You guys hear what Isaiah is saying? Do you agree? Why did we flip that inequality? It's a max now. It has a highest point, which means it's going to be able to go anywhere below that, right? Oh, so less than or equal to 7. Okay. So whenever you have a parabola that's concave down, we're going down from it, less than. Okay. Now the nice thing is, I'll start you off. You can use x's for both of these. But I want you to be thinking of what inequalities. Where's the decreasing? Where's the increasing? Huh. Every time. Good, you can make a note of that. Whenever you have a max, you're going down, less than. Whenever you have a min, you're going up, greater or equal to. What do you guys think? Can we use greater than? Oh, it won't be 2 anymore though, will it? What's it going to be now? Okay, so we know we're comparing to -3. Is it? Let's check it. That would be pointing to the right. Is it increasing to the right? No, you're falling to the right. Oh, there we go. See? So you have to ask yourself, if you're moving from left to right, and that's the only way we move with reading English and with reading math graphs. Oh, he increases, then decreases. So this direction is the increasing. So that would be, flip it. That way is the increasing part. Remember, this points to the right, to the left is the increasing part. So then what's going to go here?
Increasing.
the decreasing parts. So what did you notice about all the inequalities when the parabola switches? They all flip? Huh. Well, that's easy. So what's going on? Where are we headed? Oh, here we go, guys. Homework. Let's see if you can analyze graphs tonight. That's all I'm asking you to do. I'm going to go write it on the board. The corrections are still technically like kind of out there. If you guys right now have any corrections you want to turn in, now's the time. Get it out of your life. You don't want to lose it. The stapler is up here. Your tray is up here. Come put it in. If you have corrections, come turn them in.
Why can't you just say sorry now?
I had a few of you guys that were ready to stay after class and turn them in too. But make sure you grab down. Homework number 34, page 423. 1 through 4 and 32 through 35. Tomorrow we're going straight to notes to finish section 8.1. And then we're going to have a little factoring competition to see if you guys are truly ready to improve your test scores on Friday. Tomorrow we're finishing 8.1 and then we're having a little factoring competition to see if you guys are truly ready to improve those test scores on Friday.